Welcome to Algorush. Have you ever stopped to think about how your computer actually understands your name, or a photo, or a song? I mean, really, at the most basic level? It all comes down to one thing: translating our messy, complex world into the simple language of ones and zeros. So let's dive in and break down exactly how that magic happens. You know, it's something we just take for granted. You type your name into a field and poof, it's just there. But how does the machine actually hold on to that? How does it send it across a network? The answer to that one simple question is actually the key to understanding how pretty much all digital systems work. All right, so here's the core idea. Computers don't speak English. They don't understand the name Tom or the number 42. The only thing they get is a sequence of bytes. That's it. So the process of turning our data into those bytes is called serialization. Think of it like neatly packing a suitcase. And turning it back into something useful, that's deserialization, unpacking it. This is the universal language for all digital information. Okay, so where do we even begin? Let's start with the absolute basics, the primitive data types. Think of them like the Lego bricks of the data world. These are simple numbers, your true or false values, your basic characters. The great thing about them is they all have a predictable fixed size, which makes them the perfect place to start. So, right off the bat, we hit our first big decision: Endianness. What happens when you have a number that's too big to fit into a single byte? Well, you have to decide what order to store those bytes in. Do you put the most important part first or last? And this choice is absolutely crucial, because if two systems don't agree on the order, you get garbled data and some of the most frustrating bugs you will ever try to track down. So there are basically two camps here. On one side, you have big endian, which puts the most significant, the biggest, part of the number first. It's kind of like how some people write dates with the year first. Then you've got little endian, which does the opposite, starting with the least significant byte. Now, neither one is technically better than the other, but the key is consistency. Everyone has to agree on the same rule, or things just fall apart.
All right, whole numbers are one thing, but what about all the numbers in between? You know, the ones with decimal points, like 3.14. For these, thankfully, we don't have to reinvent the wheel. Pretty much every system out there relies on a universal standard called IEEE 754. It's like the official rulebook for turning any floating point number into a clean sequence of bits.
So let's pop the hood and see how this thing works. A standard 32-bit float is actually split into three distinct parts. First, you've got one single bit that's just a switch for the sign. Is it positive or negative? Easy. Then there's an 8-bit chunk for the exponent, which basically determines how big or small the number is. And finally, the last 23 bits make up the fraction, which holds the actual precise value. It's a really clever system that lets us represent a massive range of numbers super efficiently. Okay, so fixed size stuff is pretty straightforward, right? But the real world is messy. What about data that doesn't have a neat, predictable size, like a sentence or a list of items? Now that's where things get really interesting. So how do we handle this? Well, the most popular solution is actually beautiful in its simplicity. It's called length-prefixing. It's literally like writing on the outside of a box. There are 12 items inside. You store the length of your data as a number, right before the data itself. That way, any program reading it knows instantly how much data to grab. No guesswork needed. Let's take the name Tom as a perfect example. It's a dead simple 3-step process. First, you count the characters. 3. Easy enough. Second, you encode that number, 3, as a byte. And finally, you just append the bytes for T, then O, then M right after it. And boom, that's it. You've successfully serialized a variable length string. All right, we've handled our basic building blocks and our variable length data. But what happens when you need every single bit to count? When you're trying to squeeze out every last drop of efficiency? That's when we get into the real art form, bit packing. Think about it for a second. A single true or false value really only needs one bit, right? On or off. But computers usually like to work with bytes, which are 8 bits long. So using an entire byte for one little Boolean is like using a massive moving truck to move a single coffee mug. It's just incredibly wasteful. Bit packing is what lets us fill that truck up, using each of the 8 bits for a completely different piece of information. And here's how it's done. Just imagine a single byte is like a small panel with 8 little light switches on it. Each switch, or bit, can represent a different setting or a flag. So you could decide that the first switch means, is this a leaf node? The second switch could mean, does this contain variable-sized values? By just flipping these switches on or off, we can cram a ton of information into a tiny amount of space. So we've gone from bytes all the way down to individual bits. And you might be thinking, okay, this is cool, but why does this low-level stuff really matter? Well, it turns out these fundamental choices have a huge direct impact on the speed, the cost, and the reliability of basically every piece of software you use every single day.
It really boils down to three big things. First, storage efficiency. It's simple, right? More compact data means you need fewer hard drives. That saves money, it saves energy. Second, access efficiency. Smaller data is just plain faster to read from a disk and takes less time to send over a network. That's what makes apps feel snappy and responsive. And finally, and this one is massive, cross-platform compatibility. When everyone agrees on these rules, a system built by Apple can reliably talk to a system built by Google. These aren't just minor tweaks. This stuff is the foundation of high-performance, interoperable systems. So there you have it. We've pulled back the curtain and demystified how data gets turned into bytes. We've seen the rules for numbers, the strategies for text, and the clever tricks for getting maximum efficiency. Now that you understand how data is structured at its most fundamental level, how does that change your perspective on the software you build and use? What trade-offs between space and speed would you make now? It's a fascinating question to consider.